It's great to be back to Haskell Exchange. Last year, we had a talk without the labeled part in the title. It was just about algebraic graphs. And I got lots of feedback from the community here and elsewhere, and lots of help. And we had one of the main questions that was asked after the talk and later on is how do we add labels to what I presented last time? And here's an answer. And this was worked out together collectively. There was a big issue in the GitHub repository where there were lots of different approaches discussed. And in the end, we figured out a relatively simple way of adding labels, which I think surprised me by the fact that it was quite simple in the end. So before I start, can I ask, so how many people were here last time on the talk about algebraic graphs? Right, so only a few hands. So good, because I will introduce algebraic graphs from the beginning, and then I will add how to extend this. First of all, apparently if you Google for algebraic graphs, you get something completely unrelated to my talk. Lots of charts, kind of with functions on them and with labels on them. And this is not what my talk is going to be about. My talk is going to be about graphs, like these two graphs, for example. On the top, we have a directed graph, which doesn't have any labels on edges. This is what we talked about last time on Haskell Exchange. And on the bottom, we have a graph with some edges, labels on edges, right? So these are, in this case, distances expressed in minutes. So how much time it takes to go from one city to the other by train. And I very frequently travel from Edinburgh to Edinburgh or to London from Newcastle, right? So we want to be able to express, to represent graphs in any functional, in any language. And in functional programming language, we have a few different ways of doing this. And I'm going to present an algebraic approach for this. And so what I didn't have last time is this bit. This is new. And also, I want to emphasize that in the graphs I'm talking about, there are no sort of ports. So for example, if you're thinking about circuits, in circuits, they can, a node, a vertex, can have differently named ports. So I don't have this. Like you can connect like to a vertex, and that's it. You don't name the connection anyway. And there are no forbidden edges, which you might sometimes have in other cases. Like for example, Petronets, there are like two different types of vertices, and you're not allowed to connect a place to a place and transition to transition. So this is a sort of untyped version in this sense. OK, so let's go ahead. So first, I'll start talking about the basic kind of version of this without edge labels. A very common sort of way to represent what a graph is in mathematics is to think about a pair of two sets, a set of vertices, V, and a set of edges, E, right? And there is usually this side condition, which sort of makes sense. You don't want to have an edge without its endpoint in the set of vertices, right? So this sort of some consistency condition on the side. As is an example, a graph with 3 nodes, vertices 1, 2, 3, and 2 edges, right? So we can sort of encode this in Haskell as we do it in other programming languages in this like sort of straightforward way. So we map directly the mathematical description, a pair of 2 sets, to a pair or a product type of 2 sets of vertices and edges. And it's not really difficult to now work with this representation. You can, for example, create this example graph like this. I'm using the overloaded lists extension here, but just for clarity. But essentially, you can work with this representation as you do in other programming languages. So why do I want to come up with a new representation? I was bugged by this for a long time because I write a lot of graph algorithms, and pretty much all of us, whenever you have a data structure to represent any graph, like directed, undirected, labeled, or unlabeled, you end up with having some invariance in your data structure that sort of captures this consistency in some way or another. So I didn't capture this consistency invariant in my representation, which allows me to sort of create this non-graph in this like, straightforward implementation, right? So this 2 doesn't appear in the list of vertices. So mathematically speaking, this is not a graph, but this is not captured in types. And it's actually quite difficult to capture this in types. Well, you can do this using various extensions that I proposed. For example, previously, we had a very nice talk by Jasper, who was talking about using dependent types to verify heaps. So fantastic talk. But I would like to try to avoid going into this territory, right? So instead of sort of fixing Haskell in the sense that extend the Haskell, make it easy to represent such side conditions by, for example, introducing dependent types, I would like to propose a different way of looking at graphs, which like sidesteps this issue completely. which sort of removes this partiality, inherent partiality from our representation. And this is this sort of solution, right? So this is a data type which you can use to represent graphs. No, you don't necessarily have to use my library, which I'm going to talk about. It's a very simple data type. You just define it, and any expression sort of represented as this sort of simple language, so it's sort of like a small DSL for kind of building up graphs, corresponds to a graph, and you cannot create a sort of incorrect graph in this way. And any graphs can be created, right? So this is a very kind of minimalistic language for kind of building up graphs, for composing bigger graphs from smaller pieces, and then kind of maybe deconstructing them in some way. This is sort of is a translation of some of the work we've done in hardware design. So in hardware design, sometimes you want to be able to prove certain properties about your circuits, and we sort of came up with this idea how to represent circuits using this algebraic style. And sort of at some point, I translated this to Haskell, and I thought, oh, actually, it works pretty nicely in general, just for working with graphs in a functional programming language. So there are 4 constructors here, right? So let's look at what these constructors mean. So the first 2 are relatively straightforward. The empty graph, there's nothing in this graph, and I'm going to sort of have this kind of meaning of our expressions represented in the usual notation. So the meaning of the empty graph is not 2 sets, the empty set of vertices and empty set of edges. Vertex creates a singleton graph where you only have given a label, A, you sort of wrap it into the graph type and create a graph with a single vertex and no edges in it. Now we can combine these primitives, empty graphs and singleton graphs, in 2 possible ways. There are 2 operations here. One I'm calling overlay, and I'm going to denote it with plus because it sort of behaves similarly to addition in many ways. What it does, it just, given 2 graphs, it takes the union of vertices and union of edges. And there is no restriction on whether the union can overlap or not. So in this case, we have Q and S appearing in both graphs. That's absolutely fine. So you can take any 2 graphs and overlay them and get another graph back. And the second operation is called connect. And this operation allows you to create new edges. So there is only one distinction here at the bottom right corner here. You take the union of vertices, take the union of edges, but also introduce all the edges going from left vertices to right vertices, right? So here we had 3 vertices on the left-hand side, 2 vertices on the right-hand side. So we are going to introduce 6 edges from P to S, from P to R, etc. In particular, like this S appears on the left-hand side, and on the right-hand side, we will create a self loop. Right? So we sort of create a Cartesian product of new edges. So this operation also combines graph and allows us to build up new edges, because we didn't have an edge primitive, right? We only had an empty graph primitive, the vertex primitive. The only way to create edges is actually by using the connect operation. So we have these 2 operations. And if you look at the way they sort of their meaning is defined, right? There is no way to create a graph where an edge refers to a non-existent vertex, because the only place we create edges is here. So we create a product, a Cartesian product of edges here, and V1 and V2 are both in the domain here, right? There's no way to create a malformed graph in this representation. But instead of thinking about this set-based sort of semantics, meaning of our expressions, I would like now to go and start thinking about these expressions algebraically. What are the laws that hold when you write down these expressions? For example, in the way we defined it, it's sort of obvious that this overlay operation is commutative, right? It doesn't matter in which way you overlay graphs. So we want to somehow postulate this as a law. We want to say that any expression that contains an overlay, you can swap the left and right-hand side arguments. But you cannot do this in general for the connect operation, because in the connect operation, you will reverse the edges if you swap the arguments. So let's explore what are the laws that hold for these expressions in general. It will help to start looking by a few examples first. And by the way, don't hesitate to interrupt me at any time, because if you have any questions, please ask me. So these 2 operations that I covered, they are very important to understand, right? So if you have any questions about them, please ask right now, because otherwise you'll be confused at the rest of the talk. Right? So we can combine graphs in 2 possible ways. So let's look at some examples. So here I have sort of some example terms that we can write in this language, and the meaning now is as pictures, sort of. Yes?
I do have a question.
Yeah.
The previous slide?
This one?
The diagram. Yeah, for the other one.
So so yeah, let me repeat the questions. How do we know that these queues are the same, really? So we don't have to know. So what we can do in the way we describe it, so this is just a constructor. So we can combine two expressions, and we don't necessarily need to know that they correspond, that they have some vertices that have the same labels. But as soon as we start sort of doing anything with these expressions, for example, if you want to produce, like to draw a diagram of a graph, you will actually require this EQ instance on the labels. That's right. So at some point, whenever you are going to start kind of deconstructing these expressions that you wrote in this language, you have in this language, you are going to need some way of comparing labels so that you know that some labels should be sort of joined together. That's right. So it's an important point. Thank you. Right, some examples. So here we just create two vertices, so graphs containing a single vertex 1 and single vertex 2. So here we put them two together using overlay. So we create a bigger graph that has two vertices but no edges. And I'm going to use this sort of shorthand notation now, writing 1 plus 2. So it's not 3, right? It's not addition. It's a graph with two vertices 1 and 2, right? And here we sort of combine these two simple graphs using connect operation, which introduces an edge between 1 and 2. And I'm going to write 1 times 2. And again, this is not a 2. This is a graph with two vertices, 1 and 2. And an edge between them. A couple of more examples. We can connect the vertex to itself, sort of 1 squared, if you will, and this will create a self loop. And now let's look at a bit more complicated example. So we sort of create two edges, 1 connected to 2 and 1 connected to 3, and overlay the results. And here's where this equality comes in. So we need to understand, so we'll be able to figure out that these ones are actually the same. And so we can sort of merge these two graphs on the common vertex 1. This is the example we had in one of the first slides. And one of the first questions you will ask here is, can we factor out 1 in this expression on the left? So this is like a very familiar thing we do with expressions when we work with mathematical expressions. And yes, it turns out you can factor it out. And so why this is the case is because, well, you can sort of obtain this graph in two possible ways. You can create sort of two edges and overlay them and join on the common vertex. Or you can just connect a singleton graph 1 to an overlay of 2 and 3. And this will create two edges because we can connect all edges pairwise, all vertices pairwise, right? And in general, we want this to hold for kind of not just for single vertices like here, but in general for all expressions that you can write in this language. We want to be able to factor out common parts on left and right. So we want this distributivity laws to hold. So we sort of postulate this now as an sort of axiom in our language. We don't want now to fall back to the set-based representation to check whether laws hold or not. We want to postulate some laws that should be holding in our expressions. So distributivity is one of them because it's very, very convenient to have. At this point, again, some people who have some mathematical background might start thinking, okay, we have two operations, plus and multiplication. By the way, sometimes I'm meeting multiplication sign as we usually do. And they sort of have distributivity law, so maybe this is just a semi-ring. Semi-ring is a very common mathematical structure, like numbers, for example, form a semi-ring. We have plus and multiplication, and then you can open parentheses. And the answer is no. So I was thinking at some point that this was just a semi-ring, but no. The key here is that these two operations have the same identity, the empty graph. And in semi-rings, you're not supposed to have this. So what's going on? So everything sort of boils down to this law that we also have in graphs, and we don't have in numbers. And I call it this decomposition. So you can create this triangle graph in two possible ways. Again, we can always just put it together from edges, overlay edges. And this is a more interesting way. You can sort of multiply 1 by 2, sort of create this edge here. So if you can see it, so this edge, 1 from 2, and then you connect it to 3, and this creates two new arcs, two new edges, right? You can also, by the way, see that this operation is associative, so it doesn't matter what you do first. If you create edge 2, 3 first, right, and then connect 1 to it, you again get back to this triangle. So this is an associative operation, and this law we want to, again, hold for all expressions written in our language. We want to be able to break down a three-way multiplication into 3 two-way multiplications. And The intuition here is that any expression you can write down in this language, you can break it up into just very simple pieces, single vertices and pairs of vertices. And this is what it means to be a graph. Right? Any expression can be broken down into these primitives. Okay? So this is the algebraic structure we have. The top points here are exactly the same as in arithmetic. Overlays, commutative, like we have commutative and associative operations. We have the empty graph, which is identity of connect, and the multiplication distributes over overlay. But by adding this axiom, we suddenly change things dramatically, and we go from numbers to graphs. And as one of the outcomes of this is that the empty graph becomes identity of the second operation, which is very strange. In fact, you can see it's a two-monoid structure. So we have two monoids here, plus the multiplication, just like in a semi-ring, but they are somehow differently linked together. So they have a common identity operation, right? And moreover, you can actually, having this decomposition law allows you to write down some very silly-looking proofs, like 0 equals to 1. This is exactly what I mean. So the two identities actually are forced to coincide by this axiom. So how do we prove it? So 0, we can multiply it by 1 on the right. So 1 is identity of multiplication. We can also multiply by 1. Now we have this three-way multiplication. We can decompose it into two-way multiplications. And now we can get rid of these ones, because we can remove ones, its identity. We have 0 plus 1. And now 0 is the identity of plus. We can remove zeros, and you end up with 1. Right? So, well, many mathematicians will look very disturbed by this fact. Well, OK, so we have some more equalities in our algebra. Not a big deal, as long as we still have some interesting structure left. Right? We don't collapse everything to just 0 and 1, as would happen in a normal semi-ring. In our case, there is still some structure left, and this structure represents graphs. OK. You can add some other laws here. So what are these laws? For example, you can demand that the multiplication is commutative. And this suddenly gives you undirected graphs. So you can extend this structure by adding more laws into the universe, and suddenly you operate on other versions of graphs. So also you can drop the empty constructor, for example, if you don't want to be able to express an empty graph in your language. And some other interesting cases is reflexive graphs. If you don't want to, if you want sort of to always have a self loop on the vertex, or always not have a self loop on the vertex, you can add this axiom sort of in. You can no longer distinguish graphs with or without self loops. And also transitivity is sometimes useful if your graphs represent some sort of dependency information. Then if so y depends on x and z depends on y, it sort of implies that z also depends on x transitively. And by adding this axiom, now you sort of no longer can distinguish these two situations. It's exactly the same meaning in the world of dependencies, right? Both of these two expressions have exactly the same meaning now. So you can kind of mix and match these various sets of laws and obtain some interesting structures. And in particular, if you put together undirected graphs, reflexive and transitive together, you end up with just equivalence relations. So like the graph structure completely collapses down to something very sort of trivial, just equivalence classes, if you start adding more and more axioms. Right, so you can, so this data type appears to be quite convenient to work with in a functional programming language. So I'll just give you a very short overview of what you can do. Yes? Yes, so they are complete in the sense that you can describe any graph, and you can not describe non-graphs. So. Yes, that's right. You can always open parentheses and rearrange terms and end up with a normal form.
Another question, can quick spec find these axioms automatically?
I haven't tried. It should be, we should, for example, this decomposition axiom, can it find it? Yeah. Yeah, we should give it a try. Yeah, thanks. Any other questions? Because this is the end of the sort of mathematical part. Now I'm going to dive into Haskell a bit. OK. Right. So let's look into what we can do with this data structure. Right? So we can build up a library. So you can make this data type an instance of a lot of standard type classes. And they all sort of give you some interesting transformations. So functors, applicative, monad, mod plus, They allow you to merge vertices, split vertices, kind of remove vertices, which I find quite interesting. So you can sort of reuse a lot of code which is already out there in standard libraries to transform graphs. So by kind of translating down the expressions to normal form, you can implement the equality instance, and this equality instance relies on being able to compare vertices, right? There was a question about this. So we can compare graphs, and we can do some transformations. I'm not going to talk about this a lot. I've talked about it last time. You can also have some interesting syntax sugar. I'm not sure if it's a right use of the type class num, but you can make graph an instance of num, and then now you can express our example graph in this very kind of concise way. 1 times 2 plus 3. Again, it's not 5. It's a graph with 3 vertices. OK. It's probably a misuse of the type class num. I'm not sure if I should be doing this, but it's very convenient. So now, as I'm going to talk later about labeled graphs, and they have a different data structure, you can sort of now start thinking about this abstract interface in general. So you don't necessarily need to think about this data type. It may be a type class. It may be just an abstract API with a hidden implementation. How can you use these 4 constructors to create other bigger graphs? And there are a couple of examples. So here, I sort of given a list of vertices, I create a graph that contains all these vertices but no edges. It's just a fold with using overlay and empty, and I can build up the singleton vertices first and overlay them. And I'll create an edge, sort of like almost a sentence in English. So to create an edge, you connect a vertex to a vertex, so which I find quite convenient in this representation. So there are lots of primitives that I'm not going to talk about, but there's one interesting primitive, well, not primitive, but a function you can write which folds graphs. It's very similar to folding lists. Instead of taking 2 parameters, it takes 4 parameters because it sort of asks you, what do I do with the empty case? What do I do with the vertex case, et cetera, right? But what's interesting here is that, lots of graph sort of analysis functions can be written using this abstraction. For example, checking if a graph is empty. It's a fold with like empty is replaced with true and vertices are replaced with false, and then you end the result. So if there are only empty leaves in the expression, this will return true. It's important here that the arguments that you pass to this function, they must satisfy the laws of the algebra, because otherwise you may end up with having some strange inconsistent results. So sort of this is where the laws actually come in. It's where you deconstruct graphs. When you sort of want to do something with the graphs, once you build up your expressions, you don't typically care about graphs, about the graph laws at all. But once you start running some algorithms on your graphs, this is where you need to start thinking about the axioms that hold there. I'll just give you one quick example. So here are like the well-behaved folds. So you can check if a graph has a vertex or not by, again, folding empty has no vertex, and the vertex has this vertex we are looking for if there is a match, right? Like computing a vertex set is just a fold using the set, the set union and set singletons. Sort of you interpret your expressions using sets. Then transposition is interesting. You sort of interpret your expression, but you flip the arguments to connect. And this is not a very well-behaved function, but it's a useful function. So this function breaks the laws. So it sort of calculates the size of the expression. But suddenly now, so x and x plus empty are identical in our algebra, right? They represent the same graph. But these 2 expressions have different sizes. So you can observe sort of this structure of your expressions by using a function like size. And why? It's exactly because these 4 parameters we pass as arguments, they don't satisfy the laws of the algebra, right? You have to be careful when folding graphs. If you pass something that doesn't follow the laws of the algebra, you can end up with some strange-looking results like here. So identical graphs give you different results. But still, this is a useful function because we might want to know what is the size of our representation for performance benchmarks, for example. OK. Yeah, a question. Yeah. There's no way, I think, because it allows you to observe the structure of your expression, right? It allows you to count how many leaves there are, but it's not how we define the equality on graphs, right? The equality on graphs is not defined in terms of how many leaves there are, but in terms of various axioms that we have. There's no real way to fix this function, I think. It will always allow you to observe what you're not supposed to observe.
What does 4G do with cycling graphs?
Well, cycle is just any, like, represented as any other graph. You can overlay 3 edges pointing in a circular fashion, and it doesn't, so it depends on how you, on the functions that you give to the fold, how they interpret it. For example, you could just count the edges, and then you'll just get 3 as a result. Right? Yes?
Could you say something about what we can do with these kind of graphs? I mean, what's standard graph algorithms, like from definite components and get the first pattern trees and so on?
Right now, I have, yes, the question. So what else can we do? So what are other useful algorithms that we can run on this representation? I don't know about many algorithms that are sort of very natural for this particular representation, but I have a lot of algorithms that are implemented simply by converting these to traditional data structures. So this is like a language in which you construct your graphs, but then you can interpret these expressions that you write in any way you like. You can interpret them as a connectivity matrix and do and run algorithms that use this representation naturally. Or you can interpret it as an edge list and use that representation for other algorithms that are natural for it. So I encourage you to think about this representation as sort of the starting point. This is where you build up a graph from smaller pieces, but then you analyze it by converting it potentially to other representations which are more natural for other algorithms. OK, so now finally labeled graphs. This is what I promised in the title. So how do we add labels to this? So to me, it was a surprise that adding labels actually sort of simplifies slightly the representations, the language. So we go from 3 constructors to 2 constructors. And the intuition here is that we no longer need the overlay constructor because we sort of encode the lack of missing edges by using a special label. So we are going to use sort of a type E here, which will range over the type of labels. And now we have a special label, which is sort of an empty label, no label at all. And the overlay will correspond to connecting graphs with this non-existent label. So we no longer need one of the constructors, and we need one other parameter to the connect operation. Right? This is the whole change from going from unlabeled graphs to labeled graphs. So what are these labels now? So these labels now, we also want them to have some structure. So we want this 0, for example, to be a label. And we also want to be able to compose so labels in parallel. So in this example, labels correspond to distances. And if we have 2 graphs like here, like with distances 3 and 5 between x, y, and y, z, and a graph with distance 2, and there is a missing edge here, so it's sort of, in this case, it's like if we are talking about distances, then missing edge corresponds to infinity. So how do we want to be able to compose these 2 graphs with an overlay? But this forces us to have some sort of operation on edges, on edge labels. And depending on how you interpret your labels, you will have different operations here. So for distances, 0 corresponds to infinity. So there is no edge or an edge of infinite length in your graph. And then how do you compose distances? By just taking the minimum, right? So if you have, in this graph, you have distance 3. In this graph, you have distance 2. You pick the shortest road. So you shortest edge, and you take the 2 in the composition, right? So you can, if you sort of building up graphs from smaller graphs, it's like building new roads in your kind of transportation network if you're talking about distances. But there are other interpretations. If you are talking about capacities, so now if, for example, you care not about how fast you get from one city to another, but for example, whether there's a motorway between them, or is there just a very very narrow road which you cannot use even for your car, then you might be talking about capacities, and for capacities, the 0 is just 0. There is a 0 capacity connection. And the plus, so it's the way we compose these capacities, is just the maximum now instead of minimum. So you want to take the maximum capacity road, for example. There are also other interpretations like regular expressions for which, so 0 connectivity means no way of going from one vertex to another in terms of some kind of language of actions you can take to reach from one point to another. If you are talking about some automata, for example, finite automata, the labels there are sort of words we can write in our language. So this is the empty language. If there is no way to reach from one state to another, there is the language of possible ways is empty. And plus corresponds to or combination, right? So we can have kind of different ways of reaching your destination. What we want to stay sane, we want this operation to be associative and have 0 as the identity. And here is our next monoid, right? So we had 2 monoids, sort of for kind of building up graph structure, the skeleton, and now we have one more monoid for composing labels, and we are not done yet. We will need one more monoid. So overlaying edge labels graphs, you don't have this constructor, but you can always write a function overlay that takes two graphs and just applies connect to a zero label, right? And I have some convenient aliases 0 for like monoid empty and plus for mapend, because I'm going to introduce now 1 and multiplication as well. So to connect to labeled graphs, you just use the connect, obviously, constructor, and here is a function that creates an edge. So previously we connected vertex to a vertex, and now it takes one extra parameter here, the label you want to connect with. So now our operator is no longer binary. It's a bit inconvenient. We now need to use some sort of ternary-ish notation like this. I'm not sure if you can see it. So x connected to y with a label e, right? So it's a bit, becomes a bit awkward to talk about associativity of this operator. But if you fix one particular label, so if you're connecting with label 10, then it's still an associative operator. So you can connect with 10, and you can place brackets anywhere. But if labels are different, it's no longer associative. So I probably need to speed up a little bit. So we also want to be able to compose labels in sequence. It's also very useful in many situations when you want to think about notions like paths in graphs. So what does it mean to traverse this edge and then traverse this edge? If you're talking about distances, this means you have to spend the sum of times to go from x to z. So you can think of, now, if you add sort of transitivity axiom to this world of distance graphs, now you have this equality. So if there's a graph with distances 2 and 5, it's the same as having a graph with also a transitive connection of length 7, right? And we are going to denote this operation for composing edge labels sequentially, like angle brackets and dot. I would have preferred to use multiplication, but it's like taken over by applicative, so I'm using the dot operation here. And the identity for this operation is going to be denoted as 1. And again, don't forget that this 1 corresponds to different things depending on what are our labels. If our labels are distances, for example, this is just 0. So this is the empty path has length 0 in terms of distances. But if we are talking about capacities, then the empty path has infinite capacity, right? You can, it's like an infinitely wide motorway. And regular expressions, the 1 is just the empty string. So you can reach from a state to a state by doing nothing, essentially. OK, so I now look at a few examples, but the main one of the points here I would like to make is that this is the fourth monoid we have. So we have 4 monoids in our world. We have 2 monoids for creating the structure of graphs, and 2 monoids for combining labels, sort of the payload on the edges that we have. And the 2 monoids we have for labels, they do form the same ring, right? So the monoids for the structure, they don't form the same ring, but these 2 monoids, they do form a same ring. And we can use a lot of theory and algorithms developed for graphs labeled with same ring labels. So this is very common, in fact. There's a very nice paper by Stephen Dolan called Fun with Same Rings. It actually explores this topic, but looking at it from the matrix perspective, so connectivity matrices. All right, so another interesting observation is that the unlabeled graphs, so what we call them unlabeled, well, actually, in this formulation, they are labeled by Booleans, right? So we don't necessarily need this data type at all. We can just use this data type, and we could obtain this one by just using Boolean labels, and then 0 corresponds to the lack of an edge, which is connected by false, and the 1 corresponds to being connected by true. And sort of to combine labels, we use or and and. Sort of this captures the connectivity information. So you can combine 2 true labels into 1 true label between further apart vertices. So these are like all 4 monoids in action. So we have overlay, connect, plus, and multiplication on edges. OK, so like a couple of examples in the end. I'm not sure how much time do I have left. 5 minutes. OK, good. Perfect. So a couple of examples of edge-labeled graphs. So this is the route I often use, this East Coast network, rail network. So for example, it takes 170 minutes to reach London from Newcastle. So these are distances in minutes by train. How can we represent this? So we have a data type for cities. So we can create a kind of network type alias for graphs where labels are sort of from the distance monoid. So I'm not showing the implementation of distance, but it's just a wrapper around the underlying data type with some operations like how you compose labels in sequence and in parallel. And so the graph itself can be now an overlay of these three edges, right? So we just list our edges using this ternary operator, and this creates a graph for us. This is a different network. This is a ScotRail network that connects Edinburgh, Glasgow, and Aberdeen. In this case, we have an interesting situation where there are two different paths you can take, and they take different time. And we can sort of still express it in our small language. What we can also do, we can sort of algebraically prove that this can be simplified, right? So by just so there will be this law that you can compose edges with the same endpoints by applying the operator we use for parallel composition of labels, right? So we can say, well, this actually for the simmering of distances, this is exactly the same as this expression. It doesn't make sense to have this longer road if you all you care is how fast you can get from Glasgow to Edinburgh. So we can also kind of put together two of these networks using the overlay operator. So we can combine structures, and this also takes care of combining the labels. So this is what we get after we combine, and then by sort of reasoning using the laws we have from graphs, we can sort of simplify this, right? So apparently, ScotRail is a bit faster than a northeast rail between Aberdeen and Edinburgh. So we collapse these two pairs of edges into a singleton edge. And now we can sort of start adding more axioms again. Like in Andrey case, we can sort of distances are sort of transitive, right? So we can add transitivity, and the graph before and graph afterwards, they are the same in this language, right? Up to this transitivity axiom. So it allows you to kind of combine edges. If you go via y, you can sort of add another transitive edge that has the sum of distances on it, right? So we can, again, sort of algebraically prove that these that expressions corresponding to this graph and this graph are identical in this language by just applying the axiom of transitivity. And when we think about distances, there's also this reflexivity there. So you can always go from Glasgow to Glasgow, taking the road of length 0, right? So there's another. So if you remember, there was a reflexivity law for undirected graphs. Here it's modified by having the 0 on the edge. Okay, so another final example is automata. It might look a bit different. So now we're going to have a coffee break, and well, if you had to pay for it, so what could you do? You sort of you are presented with a choice, coffee or tea. Then you can pay if you're happy, and you're filling up the corresponding representation in the library. Or you can cancel at two different points. You can cancel and make a different choice, or you can cancel altogether and you just don't want tea or coffee at all. So this is how we can express it algebraically, well, in the Haskell library. And I like to point out here that I'm using, again, this overloaded list notation. So this sort of converts this to a set or to a regular expression. And if we apply the transitivity, so we do some sort of closure, we can observe that in the resulting graphs there are some more complicated labels. That, for example, you can go from payment to payment, not just by doing nothing, but actually you can do like an infinite loop here, deciding what you go for and then canceling, right? So this is like a regular expression for what you can do from payment to payment. And if you want to go from payment to complete, you can do an infinite loop. You can hesitate for an unbounded time, and then you can finally pay, or you can finally do double cancel. Right? So this is, and this you get by writing exactly the same algorithm as for distances, by just interpreting labels in a different simmering. Right? So we can reuse algorithms across different interpretations here. Okay, so there's a couple of points here about the libraries. The library is on GitHub, on HaskellX. It's been there's a paper about the unlabeled version, which I encourage you to read. So parts of it has been proven in Agda, but we have lots of quick check properties, and maybe you can now extract something from these properties. And these properties are very easy to write because we have this algebraic structure. So basically, any law you might have, you can just add it to your quick check suite. So this is very convenient to test this library. But also we had this Google Summer of Code project that developed a kind of comprehensive benchmark suite that compares various libraries we have in the Haskell ecosystem. You can have a look if you are interested in picking up the library which for your particular use case. Obviously, there is no single choice which is fastest, for example, for all cases. Depending on what you want to do, you will choose one of them. There are also lots of like rewrite rules that allow you, that follow this algebraic laws and allow you to sort of, for free, get efficient implementations for like composing different operations together. Okay, I don't think I really have much time to go through the benchmarks, but just one quick note that depending on the operation, the library can be very fast, so faster than even the containers library, which is very optimized, has like a memory-packed representation of graphs. It can be even faster if you add stuff, like if you're building graphs, it's really fast, it's just composing sub-expressions together. If you're deconstructing these graphs, it can be very, very slow. So here we have an example of multiple orders of magnitude slower for checking if there's a vertex, but it's a bit of an unfair benchmark because in containers, vertices are always consecutive integers, so checking if a vertex belongs to a graph is just checking if it is just two comparison operations. So obviously it's very hard to beat this because here it's like we have to traverse this whole tree and find a particular vertex. What's also interesting, because we can be so fast when creating a graph, this is a purely kind of lazy expression. So you don't necessarily need to create the complete graph before you can run your algorithm, so there is some fusion going on. So if we benchmark creation plus destruction of the graph, we get much more competitive with these libraries. So we are no longer this like multiple orders of magnitude difference. In many cases, we are faster than even containers. So this is encouraging to see that we get some payoff by being completely lazy in our representation. OK, so why not use this library? Because it's an entirely crazy new way of looking at graphs, and pretty much any algorithm you want to use, it's a new, but probably an interesting research problem. You can, of course, always kind of convert to existing representations and use textbook algorithms that are there, but it's not that much fun as coming up with algorithm that works directly on this algebraic representation. So if you want performance, you can have a look at containers. It's mature, it's zero dependencies, it's bundled with GHC. If you want another interesting graph representation, it's an FGL library. So FGL stands for Functional Graph Library. And some of the algorithms, like breadth-first search or depth-first search, they can be very naturally expressed in FGL representation. So I don't have anything like this in my library, unfortunately. So if I need to run depth-first search or breadth-first search right now, I simply convert this tree representation into one of these formats and use existing algorithms. But it will be very nice to find out how to do depth-first search directly on the algebraic representation. I don't know how to do it yet. OK, that's all I wanted to say. I have like 2 questions for you, like to catch me afterwards. Have you ever seen this axiom anywhere at all? Because I think it's an interesting axiom. I haven't come across it anywhere. Maybe it appears in some other contexts. And yeah, I need lots of help because there's lots of interesting research questions. And maybe somebody from the audience can help me with. Thank you very much.
OK, so we have 2 minutes left, so time for one question maybe, if there are any.
Yeah, so if you add an additional axiom, let's say transitivity, then yes, you can prove that 2 graphs are the same. But can you? Is there a nice way to apply the axiom many times and know that you've applied it as many times as you can to get the kind of the most like the minimal or whatever, the best graph coming out of that?
Right. It depends on your perspective on the best. Like if you want, for example, the complete transitivity information, so which sort of like the transitive closure, then there are some algorithms that are developed for like star semirings that, for example, Floyd-Warshall-Kleene algorithm that essentially tells you that you can like apply the transitivity globally n times if there are n vertices, and you reach this sort of fixed point. So there are algorithms like this. But if you want to go the other way around, which I'm, for example, interested in finding the smallest possible representation for a graph, I don't know. So it's like transitive reduction. So I don't know of any classic algorithm that does this for you. So for like labeled labeled graphs. There are algorithms that do this for unlabeled graphs, which are kind of pretty straightforward. But in the labeled case, I don't know. Maybe there are some, but I don't know about them.
All right, thanks very much.
Okay.
Sorry, we're out of time. Thanks, Andrey.
Thanks.